Hello, welcome again to Theory and Applications of Ground Vehicle Aerodynamics. Lest we forget, we will always have this come up to remind us of the raison d'etre. The primary goals for the study of ground vehicle aerodynamics, the reduction of aerodynamic drag, which provides tangible benefits that add to the value of the vehicle. The immediate one is the better fuel efficiency. There's also improved vehicle performance and increased passenger comfort. And there's also the reason of improvement of vehicle safety, which is fundamental to the value of a vehicle. So we'll always bring that up to remind us of the reason we're studying this. In this session, we'll be looking at experimental aerodynamics for ground vehicles, and we'll touch on computational methods. The experimental aerodynamics essentially consists of wind tunnel testing and track and road testing, and the computational methods come after. They usually build on well-established experimental results. Wind tunnel testing. Okay, wind tunnel. Well, a wind tunnel is essentially a controlled environment where airspeed, flow direction, temperature, other variables are not influenced by the outdoor condition. You control the test condition to your soothing, and you fix the object, in this case the vehicle that we're trying to test. This is fixed, and the air is being forced to move. That's the exact opposite of what happens in real life. In real life, the vehicle is moving relative to the air. Here, the air is moving relative to the vehicle. And the important thing is there's relative motion, and the results are matched adequately. Wind tunnels have been very invaluable in being able to predict real-life occurrences in a number of equipment, especially in vehicles. Wind tunnels are classified in different ways. These are just some of the classifications: architecture, speed, and air pressure. The classification also gets in the form of open circuit and closed circuit, and that's under the architecture classification. An open circuit wind tunnel is essentially this one. You have the flow go in and one way and come out the other way. This is a suction fan. It's pulling the air. So this fan is pulling the air as far as it can reach from here. The air goes through the honeycomb, which is a flow straightener, and goes into the test section. This is where the equipment, the calibration equipment, the probes are centered, because this is the test section where the vehicle is put. So the flow goes through the contraction cone, and it's straightened, it's parallel in the test section, and it widens up in the diffuser, and then it goes to the power plant, which is the device that's sucking the flow. Then we have the closed circuit wind tunnel. This is the closed circuit wind tunnel, which we saw earlier on. The air, this same air that's pulled in, just gets recirculated, and there's no new air coming in. This open circuit wind tunnel it's a lot simpler, as you can see, than this, but it's got the disadvantage of having to be refreshed all the time. Think of it this way: in a car, if you in some cars you have the heater being recirculated. There's a device that allows you to recirculate the heater, the heated air, and you can also have the air coming in fresh each time. This is like having the air coming fresh each time. So what happens then is this is always subjected to the outside condition. If the outside condition changes a little bit, it might affect this, the reading that you have in here. But here, after it's run for a while, there's more consistency about in the condition of the air, that is, until it heats up. So for quite a while, the air that's circulating here is of a more reliable consistency than the air that's circulating here. But then this is more expensive and more difficult to maintain. It calls for more power than this does. So there are benefits there, and there are disadvantages in each one. Just look at the optimum design. One of the things that we've indicated here is for the open circuit and for the closed circuit, we talk about open jet and closed jet. Jet is essentially the test section. So this is the jet here, the test section, and this is a closed jet, and this is a closed jet in both cases. This is an open jet. So the test section is essentially open, and it's got its benefit. One of the benefits of the open test section is accessibility. The test model is easily accessible. Also, as we will see later, there's no boundary layer buildup on the test floor, which happens. The boundary layer buildup happens here and happens here in the closed test sections. So that we'll look at those and we'll address those. You have for the closed circuit, it's an open jet or a closed jet, as we've indicated. For the open circuit, you can have partially open jets also. And what we mean by that is you could have just the tunnel floor open. You could have one side open and the other three sides are closed. You can have the top open. That is in the open jet, and that's why we talk about a partially open jet. You can have completely open jet, or you can have partially open jet in the test section. Wind tunnel can also be classified by speed. There's subsonic, transonic, supersonic, and hypersonic wind tunnels. It's difficult to see a hypersonic or supersonic wind tunnel as wind tunnel in the way we know it traditionally, because it's not this relatively cumbersome things that we have in the subsonic. But hypersonic wind tunnel, they're assembled, disassembled, because they operate for just a few seconds actually, because of the conditions surrounding the operation. But for the purpose of ground vehicle aerodynamics, we will stay essentially with subsonic, which is the most common types of wind tunnel that you will have. What do we mean by that? Well, subsonic speed maxes out at 0.8 Mach number, which is about 610 miles per hour. Primary type of interest to the ground vehicle, the primary type of wind tunnel that's of interest, like I said, is the subsonic wind tunnel. It's essentially actually the low-speed subsonic wind tunnel, because many times we hardly get close to Mach 4, so we will be working typically with the low-speed subsonic wind tunnel. Earlier on, when we had drag, we looked at air force, and we looked at the different types of air force. The big teardrop in the front, that is a subsonic type of design, rather than a sharp leading edge, almost sharp, very small radius leading edge, which is for supersonic or transonic. Transonic is essentially a stage between subsonic and supersonic, and it's in the range of Mach 0.8 and 1.2, it's when transonic ranges are considered, you have dynamic similarity matching for the Mach number. And we'll talk about, we did talk about Reynolds number, which will be looked at when models have been matched. That's essentially a given for the testing, even at very low speed subsonic testing. but as the speed increases, high-speed subsonic to transonic and beyond Mach numbers are considered. But these are just included for completion. This is the range of our operation. This is the range. Actually, this is what we will be doing mostly in wind tunnel testing. Other forms of classification of wind tunnel is by air pressure, now referred to as atmospheric wind tunnel. And the atmospheric wind tunnel can have open test section. Helps to, that's one open test section, helps to reduce the buildup of boundary layer, as we indicated in the open jet test section that was described earlier, and it dissipates turbulence buildup as flow approaches the test section. Then we have variable density wind tunnel, which is essentially a pressure vessel. It increases density to attain desired Reynolds number. Recall that our Reynolds number is our Reynolds number equals rho VD over mu. So one of the ways we can increase our Reynolds number is increase the speed. This is usually fixed. The nominal dimension is fixed. Increase the speed or increase the density. Well, you can only increase the speed so much. In fact, in most of the wind tunnel testing, we do not have a matching Reynolds number for dynamic similarity with the real life vehicle, because to do that, we would have to increase the speed tremendously. Well, problem. As you increase the speed, you're increasing the tendency, the vibration tendency for the wind tunnel. And if you include that vibration in it, it affects the results. So you don't want a wind tunnel that starts to become a vibratory specimen. So one of the ways to increase the Reynolds number, short of increasing the speed, would be to increase the density. And that's where a variable density wind tunnel becomes important, because increasing the density, you can achieve the same goal of increasing the Reynolds number to match a real-life Reynolds number. So that's one benefit of variable density wind tunnel. Let's talk about wind tunnel quality. The quality of a wind tunnel is defined in terms of the range of Reynolds numbers and Mach numbers that it can run. Remember, we defined Mach number earlier on. Mach number is essentially the ratio of the speed of an object to the speed of sound, where A is the speed of sound. So if something is going at the speed of sound, it's got Mach 1. So you can see the car was referred to as Mach 1. It's really not Mach 1 because it did not come close to the speed of sound. But the point that was being made is that it's a fast car. So V over A is the Mach number. And so when we talk about the quality of a wind tunnel, we're referring to, among other things, the range of Reynolds numbers that it can cover and the range of Mach numbers that it can run. The broader the range, the higher the rated quality of the wind tunnel. Wind tunnel quality is also expressed in terms of turbulence level of the testing equipment. You want very low turbulence level. That way you can have results that are not filled with noise, which is what turbulence generates in your result. So the lower the turbulence for a given speed, the better the tunnel rating. Also, the more readily available and accurate equipment employed for the tunnel, the better the tunnel rating. That's the ease of calibration of the test tool or the model in the tunnel. The more readily available and accurate the equipment to do these data collection are, the higher the rating for the wind tunnel. So we move past the design and function functional description of the wind tunnel. What else do we do with the wind tunnel? Well, wind tunnel I described in terms of the maximum speed. Wind tunnel is rated by the maximum speed that it has there. There aren't really many wind tunnels in the world that are well known. Well, it depends on what you say by many. We have probably about 50 or so, but it's not. It's a lot less than the number of cars, that's for sure. It's a very time-consuming, intricate thing to design, and some centers have improved, have actually almost perfected the efficiency of the wind tunnel, that people travel from one part of the world to another just to use the wind tunnel, especially wind tunnels that are designed for automobile. So wind tunnels, the parameters that I use to describe them include the maximum speed of the test section, the size of the test section. Certainly, the larger the test section, the greater will be the rating of the wind tunnel, because with a smaller test section, you are essentially limiting the size of the model and the range that can be tested. And of course, the power that drives the motor. The higher the power without vibration, the higher the rating for the test section, for the wind tunnel. Here are some comparison. Wind tunnel, in wind tunnel quality, here are some of the things to look for comparison. Open circuit wind tunnel, they're inexpensive. We saw earlier on the open circuit wind tunnel. It's just essentially it's a Venturi design. You have the flow narrowing in from the honeycomb and opening out after the test section. They're good for flow visualization of smoke and exhaust. You readily see the pattern. More kind of like qualitative than quantitative. Maintains a constant test temperature over the test period if ambient conditions are stable. If the ambient conditions are not stable, then you can't maintain a constant test temperature. So it depends. It's dependent on the environment, actually. So there's a little bit of a question mark here, because the environment outside, how stable it is, if that is consistent, then this will be consistent also. This point is made in comparison with the closed circuit wind tunnel that has been run for quite a while, where the circuit heats up. That's the point that's been made here, not so much that the temperature is constant throughout, because it's dependent on the change in ambient condition. Okay. The disadvantages, they include the fluctuating ambient conditions that affect the free stream air. The noise from the drive fan is not contained in open circuit wind tunnel, and it requires more power than a closed circuit wind tunnel to drive it, because it keeps pulling the air that is coming in from the outside without. It needs to refresh itself all the time. The power is sucking fresh air each time. For closed circuit wind tunnel, it requires less energy to drive the fan. It's insensitive to ambient conditions. It's more expensive, and there can be accumulation of smoke when used as a smoke tunnel. The build-up temperature and long duration testing. So these are disadvantages. So these have to be weighed. In a number of tests, actually, the open circuit wind tunnel will do the job. It will do the job just fine. Perhaps when more detail is required, one can go into closed circuit wind tunnel, pressure tunnel, or other forms of tunnel. This has been very successful in a lot of tests, and it will do just fine. And it's also easier to work with. I want to say portable. If you can think of the portability of a wind tunnel, if there ever is such a thing, it would be the open circuit wind tunnel that would be the portable one. a few more comparisons, benefits and disadvantages of common test section. We talked earlier on about the circuit itself. Now we're talking about the test section for any given circuit. The test section can be closed jet, open jet, semi-open jet, adaptive walls, slotted walls, combination walls. Well, we've talked about the closed jet and the open jet. The semi-open jet, again, it's partially open. It could be half open. It could be three-quarter open. It could be one-quarter open. Because typically your test section, they are considered a square. Your test section doesn't have to be a square, but when I said three-quarter, one-quarter, we're looking at a standard test section, which are usually something like that. And it takes different form. You can have there's nothing that stops one from having a circular test section, but it might be difficult to place a test, the test model in it. It depends on what one requires to test and the function of the test section. Some test sections have adaptive walls. They are less sensitive to blockage, the adaptive walls, and that's one benefit. But they have limited access. They provide limited access to test section. And that's a disadvantage. Slotted wall test section is insensitive to blockage. You have a slotted wall test section usually for the closed test section. And what happens is in the slotted wall, air is infused in. It's like bringing fresh air in to reduce the tendency for the wind tunnel to heat up from long use. So that's the benefit of the slotted wall. So the slotted wall actually removes the disadvantage of long use of the closed circuit because it brings in fresh air when the slot is open. And usually in some of those slotted walls, the slot can be opened or closed at the operator's will. Now we'll look at wind tunnel test floor modification. Why do we want to do this? Well, we talked earlier on about the test floor in the closed jet test section. Let's look for a moment at this. This is your wind tunnel floor. This is your wind tunnel, and this the material that's been tested is here. The air is coming from here. So you have your car, and what a beautiful car. So you have the wind coming in. Well, the wind comes in here. This is a test floor, even without the wheel. If you, it's complicated enough without the wheel. So let's leave that for now. There are cases in which we'll discuss that. So you have this object here, and you put it right here. Well, as the flow comes here in the test section, because this is a wall by itself, the flow builds up. So a boundary layer builds up, not by the object that you have, but by the shear presence. By the shear presence of the test flow, you have a build-up of air already, and that interferes with the model that you put in. Let's even say you raise the model this high. If you don't raise it high enough, you could still have interference with it. So the result you'll be getting is a result that is based on this flow interfering with this surface because of the presence of this flow. So how do we address this? Well, one of the things that has been done is to raise the tunnel flow. Raise the tunnel flow. When that is done, we reduce the buildup of the boundary layer. So in this case, this is the elevated ground plane. The model is placed on this ground plane. This is the elevated ground plane. This becomes, as far as this model is concerned, this becomes the tunnel floor. Whereas the true floor is this. This is the true floor. But guess what? The wind coming here, it builds its boundary layer, but the raised floor is beyond that boundary layer. It is beyond the thickness of that boundary layer. So the influence of the boundary layer buildup on the true tunnel floor does not affect the test floor. And so we have a greater chance of getting a more reflective result of what actually happens to the vehicle rather than include what happens to the floor of the wind tunnel. So that is that is the advantage of having a raised tunnel floor. The lower the test section is to the ground, the greater is the effect of the floor boundary layer on the result, and that's what we just indicated. So an elevated plane will give a more reflective result. And another thing to do with a tunnel floor modification is when we have suction ahead of the model. Again, remember, this is the tunnel floor, so we have a buildup of air as the airflow comes. If there's suction here, the boundary layer that's building here, if it's sucked up, it just starts from scratch again, so it doesn't get to build up high. It's still there, but it's not as bad as it would have been if it wasn't sucked out before it reaches the model. So that's one other way to reduce the boundary layer buildup due to the test flow. Yet one more approach is having suction plate in the tunnel floor. So this is essentially like this one. But again, even after you pass this, the boundary layer still builds up. So to continuously remove the boundary layer buildup, there is a suction plate, so you have a few suction spots in the tunnel floor, thereby hopefully eliminating the boundary layer buildup due to the tunnel floor completely. At least that is the idea. It's not always very successful. These are expensive approaches, but these are some of the things that can be done. Modifications made to wind tunnel test section to avoid the influence of test floor boundary include the moving belt. We looked at a few methods. Yet another method is introduction of the moving belt. The whole idea is as this belt moves, say a boundary layer has been built up here. As it moves, it carries that with it, so that boundary layer does not get to increase. And this belt moves like that and goes around. So because it's not stationary, you don't have the boundary layer building up continuously on it. So whatever is built here is just carried along, and another thing is built here, so that hopefully the boundary layer that's built will not get to be very high. And let's look at what we have here. This is what happens in road condition. Actually, in real road condition, this is the floor, and depending on how high the underbody of the vehicle is from the ground, you could have something like this from the floor to the bottom of the vehicle. Now, without a modified tunnel floor, this is what we have. You have this becomes one plate, this becomes another plate, and so you have a boundary layer building up between them. The boundary layer building up due to this, and that building up due to this. And so this is what we end up generating for the velocity distribution. But with the moving belt, we generate something like this, which is actually close to this, so it tends to mimic what happens in real life. And that's why a moving belt flaw is considered just to improve the flow condition and to eliminate or at least reduce the effect of the tunnel flow. In wind tunnel testing, one of the things that we look at is the model. Okay? We build a model. It's almost impossible to test the real object because of its sheer size. And sometimes the real object has not even been built, but we have a soft engineering of it, the paper design of it, and it might be easier to just go build a wooden scale, usually about 1/5 scale of the real thing. In order to do that, we need to look at some parameters so that we can build a model that's representative of the real thing. This uses the principle of similarity. From trig, high school trig, we know about similarity that is one looking just like the other. In this case, the smaller one, which is the model we built, looking just like the bigger one, except it's smaller and it's easier to handle. Well, that which we've just described is called geometric similarity. Geometric similarity, however, is not enough to have our model considered to be adequate in mimicking the real thing. We have to have dynamic similarity also. So certainly geometric similarity is required, but in addition we'll need the dynamic similarity. And it's in that dynamic similarity that we start to talk about Reynolds number and Mach number and all those things. So generally we want a wind tunnel to have sufficiently wide test section and the model to be large enough to capture real life details intended to be captured, and yet small enough to be free from the wall influence caused by the test section. We've looked at the wall influence caused by the test section, but we'll spend more time primarily looking at the floor of the test section. But there's wall influence from all the walls in the test section. So these are all present, and they can be they become noise if they're added to the results of the test section. Now, ideally, we want to test exactly the size that we will be using in real life. But again, a model is more convenient to work with. How small do you want to make the model? The smaller it is, the less the probability of including all the details that are present in the real object. So you can't make it infinitesimally small because you start to lose some details, whether it's the mirror or it's the doorknob or those things. The smaller they are, the less are those things properly depicted in the model. So you want to make it large enough to capture those things, yet small enough to not have the wall influence in the wind tunnel affect it. So the rule of thumb is to have, so this is our model, this is the wind, the speed of the air going. So we have, this is the cross-sectional area, the maximum cross-sectional area of the object, of the model that's being tested in the test floor. This is the speed of the air, velocity at which the wind tunnel is being run, but this is the velocity in the vicinity of the test section. Because as you can see, this takes away from area A1. So what area A2 has been removed from it, so what we have left is the area over which, the cross-sectional area over which the wind is blowing. So certainly the velocity will be less in this area than it is here at the time that it enters the test section. One of the things that we compute in determining in designing the vehicle is the drag coefficient. Again, remember, we want to minimize drag, and so we want to reduce the drag coefficient. Tests that have been done indicate that the real drag coefficient is obtained by using this. The computed drag coefficient is what we get from calibration, is the calibrated value when we put a test section in there, and that calibrated value is done is done in the test section area. So the real value is obtained by this ratio, 1 minus 2 a sub s over a, where a sub s is defined as the area, this cross-sectional area, plus this ratio, again, a sub s over a squared. And that gives us a very good approximation of what the real drag coefficient is. The computed drag coefficient, the drag coefficient obtained from data in the test section, is usually higher than what the true thing is because of the presence of this blockage in it. This is called blockage. This is solid blockage. That is the presence of the very object that's been tested in it. Then we have a wake blockage. We talked about the boundary layer being built up in the test section. The result of the buildup of the boundary layer reduces the true layer that's free from viscous effect, that's free from the influence of the tunnel flow. So in addition to the solid blockage, there is the wake blockage, which is there. So the cross-sectional area that's actually available is less than A minus AS. It's A minus AS minus whatever this cross-sectional area is at this particular point. So you have a V2 prime that's actually higher than the true V2. So those are things that will be taken into account, and because of that, there's a rule of thumb of what the dimension should be, the relative dimensions between the object and the wind tunnel itself. And we will come to that later on. I'll just mention it quickly now. This, for say a unit x here, the distance from here to here will be 5x, and this 5x. So, and this will be x. That's the rule of thumb that has been tested, and we'll have that in some presentation ahead. But essentially, we want to look at the wall correction and the things that need to be taken into account. There's the solid blockage and the wake blockage. Now, we will look at mounting devices when we come back. Welcome back. Mounting devices. Well, we've talked about the model that was supposed to represent the real object, a scale model car that's supposed to represent the car, 5th scale, 1/28th scale. Well, how do we do the testing? How do we send forced air into the tunnel and keep the object there? We have to hold it. We have to hold it in place. And so the case of mounting devices becomes a major thing. And it's an entire field by itself, just the designing of the adequate, appropriate mounting devices. Again, the mounting device functions to place the model and put the model. It's recommended to put the model in the lateral center of the test section. If this is the flow coming this way. This is the test section. This is the test section. Like this. So this is the test flow. This is the test flow. So we're looking top view now of the test flow. You want to put the model so that it's here. So that this distance is equal to this distance. Okay. That way, even if it's influenced by the wall, is uniformly influenced by the wall, and it's better than having it on one side. This is preferred to having, say, the model here. So you have this distance and this distance, which are not equal. This is not equal to this. Okay, we want to do this. This is what we want. I'm going to put the model here. Okay, not this. Okay, that's essentially what that indicates. The test is leads by a boundary layer effect on the tunnel wall when we do this. Now, the diagram that you have here is a cross section of the wind tunnel of the wind tunnel test section. It's the cross section of the test section. And what has been found is that this is the free stream, that's the speed in the highest speed in the wind tunnel, the speed in the test section when the object is placed right in the middle. This is the speed variation as you go from the wall, that's the boundary of the test section, to the center, and you have pockets here of recirculating flows. Most test sections have been modified, and appropriately so that you have something like this. You have something like this, and that reduces the stagnation flow and recirculating flow that you have in the edges. But still, the trend is still that this is increasing to give you the maximum speed at the test section, at the center of the test section. Hence, we want to put the test object right there so it can experience the maximum speed that the tunnel, the wind tunnel, can produce. The object is placed using balances, and we have internal balance, we have external balance, we have different types of balance. One of them is the internal balance. In the internal balance, this is the object, the model that we're testing. Okay, this is the model itself. So this balance is rigged in with wires, strain gauge wires, put inside the model. So in this case, the model will have to be opened up. This gauge, this rigging is embedded in it, and the model is glued in, it's all tied in. So the result is happening inside the model, and that's called internal balance. And it's mounted to the rear so that all the things happening here are not influenced by this mounting, because you're taking data here, all along here, and that is why you have this mounting at the back rather than in the front. So that is essentially what an internal balance looks like. Then we have other forms of balance. There's external balance. There's string balance. There's different types. That's just an example of one of the balances that we have. How do we use collected data? Well, what data is collected in the first place? The data that's collected is typically the force, the moment, and the surface pressure. And from the force, we compute the force moment. From the force, we compute the force coefficient. From the moment, we compute the moment coefficient. And from the surface pressure, we compute the pressure coefficient. We also find the lift-to-drag ratio. This is an example of the pressure distribution on a car. This represents the pressure distribution all along here, starting from here. That's the pressure distribution, and this bottom one is underbody pressure distribution. So this is the top pressure distribution, and this is by underbody pressure distribution. There's a pressure distribution as you go along here in the vehicle, as you go from there all along to there. In the ideal case, they will both end up to be the same thing, but you have separation of flow, so they don't, but they're close, and that's how the pressure distribution is. The pressure coefficient is defined as the pressure at any particular location minus the strain pressure, the free strain pressure divided by half rho v squared, where half rho v squared is the standardizing dynamic pressure. So that's how we get the pressure coefficient at each location. Scale effect, wheel modeling, and similarity. Well, you know, in the real object, in the real car, you can start and you have turbulence right away, right from here, and before you go. Whereas if you're testing the model, it's possible that at a position, actually typically at a position in the model that's equivalent to that, that's when you standardize the dimensions, at a position that's equivalent to that, you don't have turbulence occur. So you have transition to turbulence in reduced scale model to not occur, whereas in the real vehicle it has already occurred. So how do you address that? Just building the scale does not address that. And one of the things that is done is the flow is triggered at the distance on the model that would be equivalent to, geometrically equivalent to the distance in the car. The flow is triggered at that location using some kind of roughening device so that turbulence can start at that location, because typically it will not start because the speed is not high enough. The Reynolds number is not high enough to generate turbulence at that time. Wheel modeling, stationary wheels on test floor, they obstruct airflow because they become an obstacle in the way. So if we just keep the stationary vehicles on the floor, on the test floor, we would have noise in the data. That is, the true data is not given because in real life the car is rolling and the build-up that obstructs the tire in the test section does not happen in real life. So we have to find a way to depict what really happens in real life. So that we don't have an increased drag or increased lift and hence reduced downforce. Well, downforce is the tendency of the car to stay close to the ground, to grip the ground. In airplane, we want a lift for the plane. In ground vehicles, we want a downforce. We want the car to grip the ground. That is stability, that is safety. So we want the opposite of lift. And so if we have increased, if we have a flow here that's hitting this, it's going to go back up here and it will cause a lift to the car. And that's the opposite of what we really want. This is what we want. So stationary wheels, therefore, have to be addressed somehow, or wheels in the test model have to be addressed somehow. There are different things that can be done. Raise the wheels. In any of those, it will be necessary to raise the wheels somehow. Raise the wheels from the test floor to some distance, delta M, where delta M is the boundary thickness due to the test floor when tunnel is run at its maximum speed. So you know some delta sub M. The maximum, this is our tunnel floor. This is our tunnel floor, and the boundary layer building from, remember from last time we talked about the boundary layer building on the tunnel floor. The maximum it can be, we estimate that from just running this tunnel straight by itself. So that maximum it can be, we raise the wheel above that so that what we are getting on the wheel is not influenced by the tunnel flow. Okay, so that is a way to solve this. That's one way to address the problem. Well, a number of different things have been looked at. Rotating wheels have been looked at. Blockage at the back, blockage at the front, and the best design is this. Just raise the wheels so that this delta H is at least some delta sub m, the boundary layer thickness. Okay, and that has given the best result. The one that's close to that is this, because when the flow is going on and it's not blocked here, we have a situation that is close to when both wheels are raised. But this is the easiest one, and it's the straightforward one, and it's the one that's recommended typically. But it may be easier due to design to have to raise, to have to put a block somewhere there so that the flow can be, so that the vehicle can be lifted up. And this is more representative than this of what happens in wheel modeling. Again, we've talked about geometric similarity, Reynolds number and Mach number. Reynolds number, is rho VD. Reynolds number, rho VD over mu, which is the same thing as V D over nu, because our nu is equal to mu over rho, and our Mach number is the speed divided by the speed of sound at a particular point. Those are dynamic similarity parameters. Those are, they must be matched. At low speeds, you don't need to worry about this. At Mach below 0.4, this is not really important. Even actually up to about 0.6, 0.7, one may not need to worry about the Mach number. But as the speed increases, that becomes important. So that's one of the things to keep in mind. So we want to match the geometry. We want to have geometric similarity and dynamic similarity. Geometric similarity is not enough, and there's no sense in having dynamic similarity if we've not first had the geometric similarity. And geometric similarity is just in the model building itself, just intricate manual work. And dynamic similarity is just matching the flow conditions. Now, in estimating the full-scale values from the model, it's almost impossible to run the test section at a speed that will give a matching Reynolds number. So what we do is we run the test section at the maximum speed that we can without incurring unnecessary vibration in the test section. Fortunately, experience has shown that even though the Reynolds number is not matched, the results still give something that's quite adequate and representative of the true vehicle. So there isn't really much that's lost in not having the exact Reynolds number match. Okay. Blockage in the wind tunnel should be determined preferably before a model is built so as to ensure that it's below 10%. The rule of thumb is have blockage below 10% in the test section. Let's look at an example. Here's an example. We have a 5th scale model of a vehicle. Is going to be tested in a square test cell wind tunnel that has 1.2 meter. That's the size of the test section, 1.2 meter. And the projected frontal area of the vehicle, that's the vehicle that the true vehicle itself, is 3.5 meters squared. Question is this blockage within acceptable limits? Let's say the blockage is within acceptable limit. Keep in mind, we have a fifth scale. We have the area. Essentially, we're looking for the cross-sectional area of the wind tunnel and the cross-sectional area or the frontal area of the vehicle, the projected frontal area. That's the maximum cross-section of the vehicle. So if we take those, we will, and that's the same question that we put here. Here's the rule. The cross-sectional area of the vehicle divided by the cross-sectional area of the wind tunnel times the scale squared. That is what will give us the comparison for what we want for the blockage. We want a blockage that's below 10%. So the cross-sectional area of the vehicle, we have that. We're given, that's this one, 3.5 meters squared. We have a wind tunnel test section that's 1.2 meters, and so we squared that. So we have the cross-sectional area of the wind tunnel. And the scale, we're building a fifth scale, and we square that. We get 9.72, which is just below the threshold, as long as it's, actually sometimes when it's like 12%, it's still accepted and considered. This is not, it's not carved in rock, but it gives us a guideline how close we are. But preferably we want to be no more than 10%. So this is just fine. So the acceptable value now is so this condition, in this condition that we have, we can test a fifth scale model. Another way this question can be posed is, say we have a test section of a given dimension, in this case 1.2 squared, and we have a model that, we have a car, a vehicle with maximum cross-section 3.5 meters squared, and the question would be, what is the maximum size of, what is the maximum scale model size that can be used correctly in this wind tunnel? And so in this, we know the limitation is 10%. So what we will do is we will set up something like this. We will have 3.5 divided by 1.2 squared, and we don't know the scale, so we'll call that scale x. So x squared times 100 is 10%, or this is equal to 0.1. And when we do that, we'll find what our x is. And our x will give us something that's a little greater than, because we've already done this, our x will give us something that's a little less than 10%. So if it's less than 10%, it means it's within the 10% that we have. In this case, our x squared will just be 0.1 times 1.2 squared over 3.5, and that will give us about 0. It will give us an x, which is the square root of this whole thing, and we will have an x that's about 0.2. Okay, and so that it's actually more useful in being able to determine the size of the model that you can test in the test section, because in most probability the wind tunnel is already existing, and you have the size of the car that you want to test. The question becomes, what is the model that I can test in this test section? And so this form may actually be more productive in using this relationship. Keeping in mind, though, that these values are based on the assumption that the model is centralized, as we indicated earlier on, and that the lateral distance from the model boundary to the wall is 5 times the width of the model. Remember that rule If this is the cross section, the floor of the test section, the model is here, and this is 5x from here to here. This is 5x from here to here, and this is x. Okay, so that rule is important. So those are things to keep in mind. Wind tunnel testing can be a laborious work, but it's proven to be successful over time. We'll take a little break here, and we'll come and talk about track and road testing. Okay, welcome back. Track and road testing. Well, we looked at wind tunnel testing, which is a very common way, but another way is track and road testing. Usually the track and road testing is done after most of the wind tunnel work has been done, kind of like to ratify what has been designed, maybe some fine-tuning. It's not considered the first thing to do for a number of reasons. One, obviously, is you got to have built the real thing before you do the track and roll testing, which may then actually defeat the purpose, because if you depend on track and roll testing, where's the guidance to have built the thing that you're now testing? So it's not an afterthought, but it's a secondary testing procedure, a supported testing procedure to wind tunnel testing and to computational methods. The benefit in track and roll testing is you're testing the real thing that you've built. Here are the challenges. The accompanying instrument is usually cumbersome. It's difficult to carry around. Re-instrumentation is required whenever you make a change to the vehicle. When it's slight change, you have to re-instrument, especially if that change is at the pressure ports where you're taking data. There's the inability to control the environment. What you see is what you get. You can't fault Mother Nature. You can't control what Mother Nature provides for you. You can't change the wind direction, wind speed, temperature conditions. They can just change abruptly. There's very little probability that you can repeat your test the following day, even if you do the test at the same spot, because Mother Nature has the control over that. And it requires a real-life vehicle that's already built. And as we've said, how do you build a real-life vehicle if you've not been able to collect the data that will help you to build an optimized vehicle? So these are the challenges. It would be good if one had it, the real thing, and that's probably why. That is why it's used later on and not in the preliminary stage. Aerodynamic data acquisition on track and roll testing. You collect data in suspension travel, which is a measure of the load distribution and downforce in the vehicle, and mounting probe, which measures the head, that's the dynamic head, and the air temperature. Mounting probes are used. Data acquisition, we collect data on the tire rolling resistance and on the surface pressure. We've looked at how surface pressure was made earlier on. Essentially, this is the test car, and the test car is enclosed in an almost completely covered shrouded envelope, and so that the data that's collected from therein is not influenced by surrounding environment. So as much as possible, the test car is sealed so that with the information that I've collected in the road condition is collected on the test car alone. There's some kind of seal here, little seal, another little seal, part of the effort to make sure that the car is completely enclosed. So it's shrouded completely, and you have the load cell in there. And the data that have been taken in it are taken from the vehicle as much as possible, not exposed to anything else. So that's, there's a lot that's done in track and road testing. Some tracks are built with some common tracks are used, some tracks are rented out to test road condition. Some tracks are built with the bumps and the turns that you have on the real road. But track and road testing, it's one of the ideal features for fine-tuning a design, but not one for primary work in vehicle testing. Last comes experimental method, computational method, I should say. Last comes computational method. Well, computational methods have come a long way. They've been around for quite a while, but with advancing technology, computational methods have become more effective in helping us to predict the performance of a vehicle. It used to be that there will be about 20, 30 cars that are built and meant to be destroyed in testing. They're taken through destructive testing, and there's nothing that can be done about those cars. But these days, it's ideally possible to build just about 3 cars, and in fact, it's possible to build less than that. It's possible, ideally, to build just 1 car. For destructive testing because of the power, essentially because of the power of CFD these days. So we've come a long way. The advancement of technology has helped to reduce the number of cars that are destroyed to testing before we come up with the optimum car. It should be kept in mind, though, that computational result is only as good as the knowledge material that's put in. And the knowledge material originally came from experimental work. So great as computational work is, it's still got to be kept in mind that the data, the parameters that are used were obtained from repetitive work from experimental methods, typically wind tunnel testing and some road testing data that have been collected over time. Those are the data that are put in. So great as computational work is, it could not have been the founding method. It's dependent on methods that are already existing for the input data that we put into it. The good thing about it is once you've benchmarked a computational method, you can now use it to do a lot of what-if conditions. Let's look at some of the benefits of CFD. For example, one of the typical computational methods that's used in aerodynamics, computational fluid dynamics method. If we compare, like the wind tunnel, you have the build cycle, you have to build for the wind tunnel design. To certify it, it's long and cumbersome, it's expensive to build, you have to operate full-scale wind tunnel. If you have to operate a full-scale wind tunnel, which is not really abundant, that's massive real estate by itself. So there's size limitation of the test section. The underside wind condition is unrealistic, and we looked at that with the boundary layer building, and we're having a smooth underbody in wind tunnel testing, whereas we know in the real vehicle there's wires all over there in the bottom there, and the flow is not smooth. Engine cooling is generally not considered in wind tunnel testing. Passenger compartment flows are not taken into account because the wind tunnel testing is just looking at the external flow over the vehicle. Interference of probes used in wind tunnel data collection, they have the effect. People try to reduce the effect of those by having them more at the rear, or sometimes have them in internal balances, but wherever they're present and they're not completely without presence, they affect the wind tunnel data. The shortcomings of road tests, which we just looked at, you have to rig the setup for it, which is a long process, and it requires continuous adjustment for continuously varying terrain, which you're bound to find in real life. You have to rig the setup, and that is an expensive thing to do. You can't capture a range of wind conditions because you capture what you get. You can't specify the range that you want to capture if Mother Nature doesn't give you that. The test and tester are at the mercy of the weather. It's hard to isolate compartment flows. If you want to look at what happens in a particular compartment, it's difficult. But it's not impossible, but it's difficult. But there are some places, there are some portions in the car, in the vehicle that are inaccessible. That's a realistic matter, and you can't use wind tunnel or road test to do those. Instrumentation for data collection may interfere with the environment and affect the data. Here comes the benefits of the CFD. There's reduction in the development cycle because essentially once you build the model, the soft model, which is what you build, the CAD model, you can make changes and just a little tweak in the changes. You don't have to go through a whole rehash of the process of analysis of CFD analysis from scratch. You just make some changes depending on how you build the model. It's relatively economical. The benefit of CFD is not at the beginning, it's later on, especially when we start to look at a lot of what-if conditions. It can be cumbersome in the beginning at the building the model, at setting up the analysis, at building the code. It's quite a laborious work, but over time it pays off. It pays off very tangibly. There's no size limitation as long as the computing power is not limited. What would be the limitation is the computing power. You can put in any size because it's soft engineering, it's soft build. So there's no size limitation. The dynamic environment can easily be simulated. Compartments that are hard to reach or to rig for in data collection can be modeled in CFD, and you can actually see what would happen there, since the package would already have been benchmarked to data that's known to be true. Interference of data collection material is eliminated. There's early phase production cycle pre-test planning that can be done in a CFD analysis. There's no initial hardware other than the computer that you use, but for the model itself, there's no initial hardware. It's all soft design. You don't need to procure an initial model to do your CFD work. In fact, at the inception of the design, from the design concept, you can go on straight and start to do your CFD work and modify it as you go along so that it's done in parallel. It can become, actually should be, the first thing that's done. And along the way, as models are built, the wind tunnel is being conducted, the CFD model can be tweaked with what is learned. So it's actually a co-design work between the analyst and the experimenter, and down the road tester. CFD and wind tunnel, they interface a lot more, and down the road, the road test is brought in. But the wind tunnel approach is very beneficial, and it's a lot of saving. Again, not in the immediate term necessarily because of the amount of work used in building it out, but on the long range. The steps involved in computational methods, the modeling, the meshing, the specification of the boundary condition, the solution and interpretation of results. Model is prepared for modeling. Model preparation can, as I've said earlier, it can be intensive, it can be laborious. It depends also on the solid model package that is available. Some of them are not user-friendly at all, but and some of them are user-friendly, but they don't capture intricate data. So one has to really look for an adequate modeling package, solid modeling package. To see tangibly the benefit CFD, you've got to be able to have it correlate with validated wind tunnel test results. Wind tunnel tests have been around long before the CFD work came. So they still are the benchmark. The established wind tunnel results have as a benchmark. And it's important for the CFD results to be believable. You do the benchmark, which is correlated with validated wind tunnel test result. And it should, once you get it going, you should be able to take a shorter time than wind tunnel test or road test. If it's taking the same time or it's taking a longer time, the benefit is not seen, and therefore it may not be appealing. It's got to cost less than a wind tunnel test or road test, and it does cost less down the road, but initially it may actually cost more because of the cost of the analyst and the computer time. But down the road, if the interest is just for one build and one make, perhaps the wind tunnel, the computational method, CFD approach, is not the best thing. But if a person plans to make, if a company plans to make a series of vehicles, make changes along the way, especially changes on the fly, certainly you want to use the power of CFD. And again, there's a lot of what-if conditions, what are local occurrences, some places that may not be accessible with other methods. You can address those real details in computational method, and that's a tremendous benefit, especially these days when we're looking for every little method, every little way to improve the performance of a vehicle and to improve gas mileage. There are several methods of modeling. These are established methods: the Euler method, the Euler flow method, the Reynolds average Navier-Stokes equation method, the large eddy simulation, and direct numerical simulation. This will be the big thing, the direct numerical simulation, if we ever get the computing power to reach that, because there's no approximation. The whole thing is just put into the computer and it's solved for. But right now it's still a dream in the sky, and if the power of computing can be obtained, it actually would be the easiest approach if there's enough computational power to do that. The Euler method, Euler flow, or simplified flow, those could be used probably for modeling buses, because they have straight, like the panel flow method. They are easier to use, and they can be used as first pass. Euler flow method can be used as first pass, and it can give some useful data. And after that, one can choose whether they want to use the Reynolds average, the Stokes equation method, or the large eddy simulation to model the model that one is building. Now, meshing. Meshing is essentially discretization. If you have, say you have your car like this, you want to mesh them, you start breaking the car into little segments, something like that, and you start cutting them into discretized pieces, and you form. So we have a continuous material, and now it's broken into tiny discretized pieces, and those discretized pieces, equations are developed for each of them, and the approximation used to represent the whole structure. So it's a numerical solution is an approximate method, but the smaller, obviously, the smaller these cells are, the more they represent, the more they're likely to represent the smooth continuous object that we have. So there are different methods of meshing. There's the structured meshing. Structured meshing essentially just says there's uniform pattern, there's consistency. They all seem to follow the same pattern. On structured meshing, on structured grid, structured grid, this may go this way. Here, here they go like that. You may have another form of meshing. Just there is no constraint pattern. Unstructured grid is easier to generate because then you don't have to constrain the grid generation to a particular form. It's just let the chips fall where they may. You let the grids fall where they are, wherever they may be. And unstructured grids tend to follow the body vehicle more readily than the structured one. But then the structural grid is more difficult to compute, to work with than the structural grid. Then comes the boundary condition. You have to have a good understanding of the boundary around the vehicle. What is the temperature around it? What is the airflow around it? These are intricate details that determine the results that you get. So there has to be a good understanding of the physics that's surrounding the vehicle, because that understanding is what informs the prescribed boundary conditions that's placed on the vehicle. Once you place the boundary condition, these are the hard work. Once the boundary conditions correctly have been put and on a meshed piece, it's ready for solution and it's sent in to be solved, and the solution comes out and gives us results. We'll plot the things, the parameters that we're looking for, whether it's the velocity, the pressure distribution, and we use those parameter plots to determine where we want to make modification on the profile of the vehicle. So model, create a solid model for the vehicle. Once the solid model has been created for the vehicle, choose the method that you want to use to solve. Depending on the type of design that you have for cars, you have a lot of rapidly changing body. So you probably want to use large eddy simulation or Reynolds average or some custom package that's developed in-house. For something like a bus, where there's a smooth panel for a long distance along the length of the bus, you can use Euler method. Or even panel method, the simplified method. They give solution very quickly, and those simpler methods would probably generate a result that's almost as good as the more complicated ones, like large eddy simulation, just because of the profile of the vehicle. The more intricate the profile, the more the need to use things like LES or some other in-house built packages. And once you do that, impose the boundary condition, it's very important to be sure that the boundary condition that's imposed is one that is reflective of what happens in real life. Most of the problems that's encountered after a successful modeling, which can be very difficult, and after a successful modeling, most of the challenge that's encountered after a successful modeling and meshing, most of the difficulty is in prescribing the boundary condition. And prescribing the boundary condition is a function of experience. It's really difficult to teach the boundary condition that should be imposed in every case. It's a build-up of experience. There are some common ones, like if there's wall effect, or if the temperature is constant, the flow is incompressible. But there are some others that, depending on the condition in which the vehicle is going through, that are brought in by experience. And over time, there's an accumulation of this know-how for the different boundary conditions. Once that's put in, the problem is taken into the solution mode, and the results that are of interest are plotted, and those results are interpreted to be used for affecting the design or the redesign or the improvement of the vehicle. This is just a little touch. It's just essentially a little indication of an approach that is a computational method. Just scratch the surface. It's kind of difficult to teach the computational method in just about any vehicle design, because a lot of details that are generally specific to that particular design. But these, these steps, modeling, methods of modeling, meshing, imposition of the boundary condition and solution, are essentially the steps that are taken in whichever computational method is used to solve the problem. Well, this concludes our experimental and computational method approach to ground vehicle aerodynamics. Thanks for watching.